we're going to perform some determinations of adequacy, analysis of beams. This is the first step in understanding how to do work, is to be able to check your work. And so we're going to talk a little bit today about all right, now what's your problem? Yeah, you're funny. Better? Yeah. It always helps to be able to read. So we're going to talk about adequacy of beams. In flexure. And so flexure, right, is when the beam either sags or hogs. When we have sagging and hogging, this causes stresses. So, because we're doing analysis, we already have a pre-existing beam. So let's draw our beam. And to show you how easy it is, we're going to work without a net. Let's see, we're going to have a, what do you want, a number 5 bar down here. We're going to have a width of 8 inches, depth of 24 inches. Nice 1 to 3, fairly common size of beam to see. F prime C is equal to 4 kips per square inch. F sub y is equal to 60 kips per square inch. And that's all we need. So this is our beam. Oh, we need the clear cover. Did I tell you what the clear cover is? That's the distance from the edge of the concrete to the first bar. Because if they're right at the bottom, remember we showed you they bend out, right? They'll be able to get away from the loads. We need to contain them, confine them inside. So that cover does a bunch of things, one of which is confinement. So we get our clear cover set at 2 inches. And the question is, determine the nominal and ultimate moment capacity. Where m sub u is equal to phi m sub n. So the ultimate is our reduced nominal capacity, phi m sub n. So what's the first step? We're going to collect. This is our solution, right? Collect terms. Well, I have f prime c, that's equal to 4 kips per square inch. F sub y is equal to 60 kips per square inch. B is equal to 8 inches. H is equal to 24 inches. D, which is equal to 24 inches minus the cover, is equal to 22 inches. Area of the steel. I'm sorry? Thank you. Does anyone remember what a number 5 bar, what does it mean when I say a number 5? 5/8 of an inch, right? So we could, if we wanted, take the diameter, 5/8 of an inch, multiply pi d squared over 4 to come up with the area, but instead, since they're standard bars, we're just going to look it up. So this is what the photocopier ate. So a smaller version of it, which I will put up on Canvas. I just need to find it now. What's the cross-sectional area of a number 5 bar? Area, number 5, 0.31 square inches. Okay. 0.31 inches squared, and the number of bars is equal to 1. So, it should be, and number of bars is equal to 1. So we've collected all of our terms that we need that are important. Now we have to make our assumption. We're going to say, no one should be worried. We're going to assume that F sub S is equal to F sub Y, the steel yields. Perfect. Oops. The steel yields. Once we make that assumption, now it's easy. A is equal to AS F sub Y divided by 0.85 F prime C. B, which is equal to 0.31 multiplied by 60 kips per square inch. 0.31 is in inches squared. 0.85 multiplied by 4 kips per square inch multiplied by 8 inches. It's going to give me a result in inches. Always check your units until you're sure. So what does this come out to be? Ooh, can't be. .31 times 60. Can't be. I don't.
Yeah, 0.68.
I'm sorry?
0.68.
0.68
Yeah.
inches. Wow, it's good now. The nominal moment capacity is equal to A sub S, F sub Y, D minus A over 2. I know all of those things is equal to 0.31 multiplied by 60 kips per square inch, and this is in inches squared, multiplied by 22 minus 0.68 over 2, and this is in inches. So I've got inches cubed on the top, inches squared on the bottom. I'm going to get a result in kip inches, which I don't like. I like kip feet. So I'm going to multiply that by 1, which is 1 foot, divided by 12 inches. And this will give me a result in kip feet. The only reason I like kip feet is when I do my structural analysis, the results of the beam are going to come out in kip feet. So let's run that one through. Anybody got a nominal moment capacity? Yep, 33. I got 33.6, so 33.6 kip feet. You would not, now, you got 33.5 and I got 33.6, and it all depends on how many decimal places you carry in your calculations. But because of the assumptions that are in there, neither one of us is right. It's around that number, right? 33.5, 33.6. So if you differ by a couple of decimal places, and I know there are other professors who don't have this feeling, it's engineering, construction work. We're not building effing pianos. If your numbers differ by mine in the 4th decimal place, obviously you're wrong. So long as, if you got somewhere around 33 and a half, that's good enough, okay? So don't stress out over getting exactly the same number, and that's why our assignments will be, you have to type them in, they're a little bit longhand, right? Or write them in and take a photograph with your phone and then scan that in. Show me the work, because I know what I did.
Well, I got 33.57, so I could round up.
Yeah, there you go. See, it's the same number. And so the important thing is, it's not 50. 50 is wrong, and it's not 10. But within a number, right? You're going to find out when we go to design the beams that the steel isn't available in all the sizes you want anyway. So, what do we have to do last? Check our assumptions. Exactly. So we're going to check that assumption. We know that C is equal to A over beta 1, which is 0.68 divided by 0.85. And what does that come out to be? 0.8? No. 0.78. 77. Oh, I should have stuck with my first answer. Okay. Then we know that the strain in the steel is equal to 0.003 D minus C over C, which is equal to 0.003, 22 minus 0.8 over 0.8. About 26 and change, almost 27, times 0.003. This is almost 27. Anybody got a number?
0.0795.
Yep. 0.0795, which is greater than 0.002. Okay. Assumption correct. Right? That's what that okay in the check mark means. So I checked. So now, my phi factor for this strain in the steel greater than 0.005, phi is equal to 0.9, and the ultimate moment is equal to phi times the nominal moment. Sorry, it's equal to phi times the nominal moment, which is 0.9 multiplied by 33.6. What does that come to be? 30.3?
Yeah.
30.3 kip feet. Put a box around your answer. Make you one of those stories where I had to walk uphill both ways to go to school. When I was in engineering school, you were told to put a box around your answer, and that's what the TA looked for. So if you got like about 30, you get 100%. If you got some other number, you got a 0. But show your work. Because if you get the wrong number and I can go back and say, oh, look what you did, then I'll tell you what you did in the assignment and send it back. Okay? So there's one. I don't know. Still not satisfied. Want to do another one? It's a rhetorical question. Well, I like my beam size before. So this beam is 8 inches, and this is 24 inches. We have 2 inches of cover. We have compressive strength of the concrete is 4 kips per square inch. The yield strength of the steel is 60 kips per square inch. Oh, I'm sorry. Yeah, yell at me because there is a screen here that's showing me what's up on the screen, but my hand sits over top of it. Stupid. So we got what we want. Then we need some bars in here. What do you think? How about 4 number 9 bars? Right, it's a very important beam. This is the beam that the dean is going to use, and we want it to be a great beam because we don't want anything bad to happen. So we're going to really, that one number 5 bar, it was puny. I mean, the number 5 bar is not very interesting, is it? Right? Number 5 bar, not very much steel, right? Number 9, that's an 1.25 inches in diameter. I don't even have one. And now I got 4 of them across my beam. Do you remember how we talked about concrete being intimately bonded with the steel? These are bars that have been removed from a bridge under construction or under demolition. See the concrete still stuck to them even after being bashed out with a hoe ram? 4 number 9 bars. Now you're about to find out that I love number 9 bars. Do you know why I love number 9 bars? It's not obvious. First thing let's do, we're going to collect our terms. Pretty easy. F prime C is 4 ksi. F sub y is 60 ksi. B is equal to 8 inches. H is equal to 24 inches. D is equal to 24 minus the cover is 22 inches. The number of bars is equal to 4, and the area of the steel is 1 square inch. So Mr. Professor likes number 9 bars because the area of a number 9 bar is 1.00 square inches. So it makes it one less thing that I will make an error on when I'm doing this for you. So let's, same thing, we want to compute m sub n and m sub u. So here's our solution. We know that m sub n is equal to m sub u is equal to phi m sub n, and we further know that if the steel yields that F sub s is equal to F sub y. There's our assumption. From that assumption, it all falls apart. A is equal to ASFY divided by 0.85 F prime CB, which is equal to 4 number 9 bars multiplied by 60 kips per square inch divided by 0.85 divided by 4 kips per square inch, and B is 8 inches, which is going to give me a result for A in inches. So let's see, what's that going to be? It's good practice to follow along and do the calculations on your calculator yourself, because you get used to the magnitude of the numbers. Plus, who can I guarantee you is going to make a mistake doing these hand calculations? I am, because I'm trying to do a whole bunch of things up here in my head, and I'm going to make a small error. So you need to check. Anybody have a value for A? 8.8 inches. Okay, now it's easy, right? Nominal moment is ASFY D minus A over 2, which is equal to 4 square inches, 60 kips per square inch. D is 22 minus 8.8 over 2. What's our moment capacity? And I want it to be in kip feet. Anybody have a number? 352 kip feet. 10 times what that scrawny little beam was right? But more importantly, if I look at the beam, yes, sir?
Where do you get the 4 from? For AS?
4 is the area of the steel. So there's
You take it by
4 bars,
bar.
each one is 1 square inch, okay? So N sub B, 4, each bar is 1 square inch. So we got this pretty good. That's more than 10 times the nominal capacity. But the beam is the same size, right? Beam's still 8 inches by 24 inches. Just got to check our assumption. So we need to check our assumption. The strain in the steel is equal to 0.003 multiplied by D minus C over C, which is equal to 0.003 multiplied by 22 minus 8.8 divided by 8.8. And what does this come out to be? .0045, yes. 0.0045. So are we in tension control?
We use A for C instead of C.
Oh,
We didn't solve-
thank you.
We didn't solve for C.
Remember I predicted I would make mistakes? You thought I was kidding. C is equal to A divided by beta 1. C is equal to 8.8 divided by 0.85, and that's equal to about 10.5?
10.4.
10.4 inches. So now we have to redo this die. The strain in the steel is equal to 0.003 multiplied by 22 minus 10.4 divided by 10.4. Everyone get that number? Okay. So, are we in tension control? The strain in the steel is equal to 0.0033, which in fact is larger than 0.002, right? So our assumption is valid. Right? But the strain in the steel is less than 0.005, so we're in the transition zone. And our phi value is equal to 0.65 plus 0.25 multiplied by the strain in the steel minus 0.002 divided by 0.005, and our phi factor is equal to what? right? Just falls out of that equation. We're in the, if you remember our phi factors, we're in here somewhere. Right? We're 2.33, we're about right there. So we get a value that's less than, the greater than 0.65, less than 0.9. Now, under the code analysis, this beam is inadequate. But we can still calculate the ultimate moment, which is 0.715 multiplied by 352 kip feet. And what do we get? Yeah, 251.7, 252, somewhere in there. Kip feet. Since phi is less than 0.9, which means we're in transition, is the beam adequate? Does it meet the requirements of the code? Not adequate. But you may find in a building under restoration, built to older codes, that this is where the beam is. You have to know how to analyze it. You may wonder, why am I doing all of these analyses? I mean, surely I'm just checking existing beams. And that's because every single structural calculation is checked by another person. Why do we do that? It's the obvious reason, right? What's the consequences of a mistake? One of the possible consequences of a mistake? Death, right? No different than they have if you had loaded up a gun and shot someone. Murder. And there are people who have been charged, structural engineers charged with murder because of gross negligence. All right, so the reason that we check is because it's necessary to check. And so if you look at various engineering companies will have all the same kind of paper, right? Like this piece of paper here that you're used to seeing. You never really look up over here as Baton Consulting Engineers paper. The date the work was done, the project, it should be drawn by, that's why we got a discount on them. Owned by, that was their typo, because we told them it was a D and they went ahead and printed them anyway. And then it says, check by. So, just like construction, structural design is a team. There are more than one person who looks at it, because the consequences of making a mistake are quite high, because you may not know you made the mistake until the structure has been erected. And then one day the wind is blowing really hard and it's snowing, and all of a sudden you reach the limit state that you're not supposed to have reached. So that's why we're going to check. We got time. Want to do one more? That one's not a rhetorical question. Is that, who feels comfortable about doing these? Yes, sir.
Should we do one of the homework problems?
Which one? Which one is number 3? Do you have it in paper?
I got it right here.
Perfect. Number 3. What a coincidence. Okay. How often, I use this similar assignments. I change the numbers from time to time, but similar assignment every year. So it's 16 inches square, right? 16 inches square, and I have a number 8 bar up the middle of the tie, and I want to know what's going to happen. So, have you ever wondered why professors give you assignments? Is it because we have no life and then therefore want you to have no life? or we like to have busy work. What's the purpose of an assignment? Two purposes. If I'm going to show you how to do the homework, you got to at least give me that. What's the two purposes, right?
Understand the,
Number one is to demonstrate that you understood. Number two is to teach you something. And so we're going to go through, and I will work this problem out for you. It's recorded, so they're not helping, the Tuesday guys aren't getting left out. Oh, and did I tell you that the other thing I figured out, because I'm sick and tired of Canvas, I started my own YouTube channel, like some kind of hip-hop star. And you will be getting addresses to YouTube as opposed to having to ask me permission. Okay? So let's do this. We're given a structural member. It's a tie. I'm sorry? Yep. Give me a sec. There we go. Is that better?
Yep.
And do you remember what a tie is? Right? A tie is something that's being pulled. So the question says, what's the strain in this, what's the stress in the steel?
What is the force in the steel and the concrete?
Yes, what's the force in the steel when the concrete cracks? So we're pulling it in tension, and at what stress, sorry, we're pulling it in tension, and at what strain is the concrete going to crack? 0.002. So we know that the strain in the tie, or the strain in the concrete, is equal to 0.002, right? This is the cracking strain. Right? What happens to the steel and the concrete? Keeping in mind that this bar, you can see how it was violently removed from a bridge with a little bend in it. This bar has what on it? What's the white stuff stuck to it? Concrete. So, can the steel and the concrete move independent of one another? Only after the cracking, right? Up until it cracks, they have to be locked together. So if the strain in the concrete is 0.002, what's the strain in the steel? 0.002. Because the tie cannot separate. Once it cracks, the steel can strain in between the cracks, and the concrete doesn't have to. But for right now, it does. So at that cracking point, since concrete and steel are bonded, and they're bonded both chemically and mechanically, although you can see it's pretty stuck on there. Green bar is not so much, but that one is, that the strain in the concrete is equal to the strain in the steel, which is equal to 0.002. The stress in the steel is equal to the modulus of elasticity of the steel multiplied by the strain in the steel, right? So the stress in the steel is equal to 29,000 kips per square inch multiplied by 0.002, and that is 58 kips per square inch. That's the stress. What's the force? If stress is equal to the force divided by the area, then force is equal to the stress multiplied by the area, by definition, right? The purpose of this is to check, make sure you can go back and forth between stress, strain, and force. So we know that the stress is defined as load over area. And in this particular case, Fs is equal to 58 kips per square inch. The area of a bar number 8 bar is 0.79 square inches. And so the force is equal to the stress multiplied by the area, which is equal to 58 multiplied by 0.79. And what's that? What does that come out to be?
That's not different.
Oh, shoot. Sorry,
45.8.
45.8 kips. So the purpose of that calculation is to remember you need to be able to transfer between stress, strain, and load all the time. And in the elastic region, because the strain in the steel is below the yield strain, Hooke's law applies. That make sense? Okay. So do you want to do one problem on your own? So let's take our same, let's do a different cross-section. That cross-section's getting boring. Let's do a beam. It's 6 by 18. We have a number 4 bar. The area of a number 4 bar is 0.20 inches squared. We're using 4,000 psi concrete.
Slide it down.
Yep. 60 KSI steel. And our cover is equal to 1 inch. And we want to determine M sub n and M sub u. Oops. All right, so let's all do this independently, and we'll see where we go from there. So those of you watching at home should now take some time and do the calculation and come back, so there'll be a dull screen and no concentration music because we don't have any. So, anybody got an answer? The stuff I looked at going on looked like it was being done correctly. What'd you get? See, this is lowercase a. Other than that, it's right. All right, so instead of being,
Oh, yeah, I wrote the wrong symbol.
yeah, it happens. Anybody get 15 kept feet?
15.12.
Anybody get a different number?
15.14.
So, you know what the number is? It's 15 between us friends, right? I understand that there are some professors who will tell you that 15, 15.18, and 15.04 are all different numbers. In a class called estimating, it makes no sense to me. Yes, sir.
I got 60. No, I just don't know where I was so high.
That's right. So this is right, but I got a different number
Gotcha.
when I calculate it out. I'm going to put up my solution in case you think I was being lazy or something. So those of you at home, this is the solution. So you should have A at about 0.59, 0.588, something like that. Anyone get anything not that number? Then you multiply this out, 0.2 times 60, 17 minus 0.588 over 2, and so your numbers were those numbers. So did I put it into the calculator wrong?
I got the 60.
I had the 16.8, my A was 0.44 though.
Uh-oh, how'd that happen? Yeah, that's a calculator error. Just in case you think it doesn't happen, I did it once and I got 5.88, and I said, well, that's wrong. Then I did it again and go, okay, 0.588, but now I got two answers. So I'll do it a third time, and I got 0.98, and it's like, Kevin, because you can see how I was clever. I'm going to take this, I'm smart. I'm going to take the 10 and the 6 out. So that the 60 and the divided by 6 is 10, because make it an easier calculation. It wasn't. But anyways, it comes out in the wash. Those are the results. It looks like where we have differences, it's because we made calculator errors, which is why we check. Do you know how long I've been teaching this class? This is probably, I probably taught this class 12 times. 12 times. And I missed that C is A over beta 1 when we did that problem together. Because I'm a human being. What's that? Yep. So, yeah, so 6 is the, 6 is the beam width. 8 was from the other problems. And that will always happen to me is that I'll remember a number from another problem. So that's why you want to check. But we've all got about the same result. Do you ever see a movie, what's it, Apollo 13 with Tom Hanks? Seen the movie? And at one point, they have the leak and they try to figure out, do they have enough oxygen to live? In other words, are we going to be able to get them back? And you can see all the engineers running their slide rules. And by the way, slide rules didn't give you 5 or 10 significant figures. And the first guy says, yep, they've got enough. And you watch down the mission control line, everybody else completes their calculation and says, yeah, that's right. Because people can make arithmetic errors. That and it's the only two movies where you get cool engineering things. The other one is from many years ago called The Towering Inferno. And so there's a big apartment building on fire. Probably wouldn't make that movie today. It's not quite as funny, I guess, as it was. And they have a structural engineer who's calculating that if they just open the water tanks at the top and let the water flood down, will it break the building? And he seems to be doing all these calculations, say, well, I ain't no rocket scientist or nothing, but the load's up there now, and it's not falling down. So the chances of letting the water come down, it's not going to be that much bigger of a force than it is now. But it made for good TV. So that's how to do the problem. Does anyone not feel comfortable doing these? Remember I told you by the end of the day you'd be helped, and you didn't believe me, did you? You looked at me and said, listen, pal, so this is how this whole course is going to go. We're going to start doing something, and we're going to derive it from first principles because I want you to understand that there's some mechanics behind it. And you're going to be in the middle of it saying, how the, I don't know which way is up. But we'll end up each time like this, that you're comfortable doing analysis. Okay? Anybody have any comments, things they want to mention? Parts of your other classes going okay? It's a struggle. This one's tough because I have to do the same lecture over, which is why I record the Thursday one, because it's usually just a little bit better. We'll start to look at what happens to beams when we need more capacity, but we can't make the beam deeper. That'll be what we're doing next week. Okay? So, do you check out my YouTube video, which will be